Hello my friends and welcome back to KrossUSA channel. Today we'll explore 4 incredible companies that are pushing the boundaries of what's possible with modern machining, assembly, and finishing technologies. Let's get started. We begin inside PTG Holroyd, a name respected worldwide for its mastery in producing high-performance screw rotors, the heart of compressors, vacuum pumps, and refrigeration systems. These rotors are not just pieces of metal, they're precisely engineered components that determine the efficiency, noise level, and longevity of entire industrial machines. The process starts with solid alloy steel billets, sourced from carefully selected mills for their uniform grain structure and resistance to fatigue. These billets are first loaded into a heavy-duty CNC turning center, where cutting tools remove excess material and shape the basic outer profile. The lathe's cutting head glides with precision, guided by digital programming, achieving tolerances within a few hundredths of a millimeter. Next comes rough milling. Holroyd's proprietary rotor milling machines are fitted with custom-designed cutter heads that follow a complex helical path to carve out the lobes. These lobes are what compress air or refrigerant in service, so their accuracy is non-negotiable. The synchronized motion of cutter and workpiece ensures perfect pitch and depth across the rotor's entire length. Once rough milled, the rotor moves to finish grinding, a step that transforms the surface from machined metal to a fine, almost mirror-like sheen. Here, diamond-coated grinding wheels trace the exact curve of the lobes, removing microscopic irregularities. The smoother the surface, the less friction and heat when the rotor operates at thousands of RPMs, often for years without stopping. Every rotor then goes through dynamic balancing on specialized rigs. Even the slightest weight imbalance at high speed can cause destructive vibrations. The balancing machine spins the rotor and detects any uneven mass, allowing technicians to make fine corrections. The final stage is precision measurement. Using advanced coordinate measuring machines, CMMs, every surface, angle, and pitch is scanned and compared to the original CAD model. Laser probes and touch sensors ensure there's no deviation from specification. Once it passes inspection, the rotor is paired with its matching counterpart, the male and female rotors that will interlock with minimal clearance. A light coat of protective lubricant is applied, and the rotors are sealed in moisture-resistant packaging, ready to be shipped to compressor manufacturers around the globe. From the moment the billet enters the workshop to the moment the finished rotor leaves, every cut, grind, and polish reflects decades of engineering refinement. Welcome to Horsberg & Scott, where they don't just make gears, they create mechanical masterpieces that can weigh as much as a school bus and transmit power that could light up entire neighborhoods. These aren't your typical workshop gears, folks. What you're witnessing here is the transformation of massive steel forgings, some weighing over 50,000 pounds. These forgings start life as ingots, heated to nearly 2,000 degrees Fahrenheit and shaped by hydraulic presses that exert millions of pounds of force. The material? Usually premium gear steels like AISI 9310 or 4320, specially formulated for maximum fatigue resistance. The initial rough machining happens on these enormous vertical boring mills, some with tables over 20 feet in diameter. Watch how the cutting tool removes material in controlled passes. The machine's spindle power often exceeds 200 horsepower, yet it maintains positioning accuracy within a few thousandths of an inch. That's like having a bulldozer perform microsurgery. Now we're getting to the heart of gear manufacturing, tooth generation. Horsberg & Scott uses massive gear hobbing machines for this critical operation. See that cylindrical cutter with helical flutes? That's a hob, and it's essentially a screw-shaped cutting tool. As the hob rotates and feeds across the gear blank, It gradually generates each tooth profile through a process that's part cutting, part forming. The mathematics behind this process would make your head spin. The Hobbs rotation speed must be precisely synchronized with the gear blank's rotation to create the exact tooth profile and spacing. Modern CNC gear hobbers use servo drives with feedback systems that make thousands of positioning corrections per second. The cutting speeds might seem slow compared to regular machining, but when you're removing this much material with such precision, patience pays off. For the really massive gears, we're talking 15-foot diameters and larger. They switch to gear shaping or even gear planing. The gear shaper uses a cutting tool that looks like a gear itself, reciprocating up and down while both tool and workpiece rotate in precise synchronization. Here's where the real transformation happens, though you might not see all of it. These massive gears undergo controlled heat treatment processes that can take days to complete. First, they're often carburized. That means introducing carbon into the surface layer at temperatures around 700 degrees Fahrenheit. This creates a hard, wear-resistant surface while keeping the core tough and shock-resistant. The quenching process is critical. Imagine trying to cool a 20,000-pound gear uniformly. They use specially designed quench tanks with circulation systems that ensure even cooling. Too fast, and you get distortion or cracking. Too slow, and you don't achieve the required hardness. The tempering process that follows relieves stress and optimizes the balance between hardness and toughness. After heat treatment comes the precision work. These gears often undergo gear grinding or gear honing to achieve the final tooth geometry. The gear grinding machines use specially dressed grinding wheels that can achieve surface finishes measured in microinches. Watch this gear tooth inspection process. They're using coordinate measuring machines with specialized gear measurement software. This CMM can evaluate tooth profile, lead angle, pitch accuracy, and run out with incredible precision. Every dimension is compared against the gear's theoretical perfect geometry, with deviations measured in tenths of thousandths of an inch. The final balancing operation is crucial for high-speed applications. Dynamic balancing machines spin these massive gears at operating speeds, while sensors detect any imbalance. Material is then removed from specific locations to ensure smooth operation at full speed. Horsberg and Scott's quality control goes beyond traditional measurement. They use laser interferometry for ultra-precise measurement of gear tooth spacing. We're talking about accuracy levels that rival the equipment used to detect gravitational waves. Their gear testing facility can actually run these massive gears under load conditions that simulate years of operation in just hours. This back-to-back testing reveals any issues with noise, vibration, or durability before the gear ever reaches the customer. They can simulate the exact operating conditions the gear will face, whether it's in a steel mill, mining operation, or power generation facility. From 50,000-pound gear forgings to precision measured in millionths of an inch, Horsberg and Scott proves that size and precision aren't mutually exclusive. When you need to control the flow of liquids or gases with absolute reliability, whether it's natural gas, crude oil, or high-pressure steam, you need a ball valve that's engineered to perfection. Welcome to Meccanica Gervasoni. What you're seeing is the creation of the valve's most critical component, the ball itself. Starting with premium stainless steel bar stock, often 316 or 17-4 pH stainless for corrosion resistance, the rough ball shape is first created on high-precision turning centers. But here's what's fascinating. Achieving that perfect spherical geometry requires incredibly sophisticated machining strategies. The ball undergoes multiple machining operations on specialized equipment. Notice how they use both turning and milling operations to create the flow passage? That through hole must be perfectly concentric with the ball's outer diameter, with tolerances typically within 0.0005 inches. The surface finish is critical too. Any imperfections could create turbulence or provide nucleation sites for corrosion. The valve body manufacturing showcases some serious precision work. Starting with investment castings or forged blanks, these parts undergo extensive machining on 5-axis CNC centers. The seat pockets where the ball seals must be machined to incredibly tight tolerances. We're talking about concentricity and surface finish requirements that rival aerospace components. Watch this boring operation creating the main flow passage. The boring bar must maintain perfect alignment while removing material, creating a smooth, consistent diameter that matches the ball's flow passage. The transition zones where different diameters meet are particularly challenging. Any sharp edges or inconsistencies could create pressure drops or turbulence that affects valve performance. The valve seats are where precision meets material science. These components, often made from PEEK, PTFE, or metal-to-metal designs, undergo specialized machining operations. For soft seats, the machining must be done at specific speeds and feeds to prevent material buildup on the cutting edge. The sealing surfaces require surface finishes measured in microinches, smooth enough to seal against high pressures, yet with the right texture to prevent galling. The assembly process is like watching a high-precision mechanical ballet. Each component must be assembled in perfect sequence with specific torque values and positioning. The ball must be inserted with precise timing to avoid damaging the seats. Spring-loaded seats require careful compression during assembly to ensure proper preload. Notice how they use specialized fixtures to maintain component alignment during assembly. The stem packing requires precise compression to achieve the right balance between sealing and operating torque. Too tight, and the valve becomes difficult to operate. Too loose, and you get leakage. Unacceptable in high-pressure applications. From microscopic surface finishes to high-pressure integrity, Meccanica Gervasoni proves that valve manufacturing is a perfect blend of precision engineering and artisanal craftsmanship. When you're flying at 3,000 feet in an EC-225 helicopter, your life literally depends on the precision of components like this vertical bevel gear shaft. There's no room for good enough in aerospace manufacturing. It's perfection or nothing. The journey begins with aerospace-grade steel alloys, typically AMS 6265 or similar high-strength, low-alloy steels specifically designed for aircraft applications. These materials undergo rigorous incoming inspection, using ultrasonic testing to detect any internal flaws that could lead to catastrophic failure. The material traceability is incredible. Every piece can be tracked back to the original heat treatment lot, including chemistry analysis and mechanical properties. The raw forgings are created using isothermal forging processes that ensure optimal grain flow and eliminate any weak points that could compromise the shaft's integrity under the extreme loads of helicopter operation. The machining operations on these vertical shafts require extraordinary precision. The main turning operations are performed on specialized CNC lathes equipped with live tooling capabilities. Watch how they maintain concentricity between different diameters. Any runout could create vibrations that would be felt throughout the entire helicopter. The spline cutting operation is particularly critical. These splines must transmit enormous torque from the main rotor system while maintaining perfect alignment. The spline profile is cut using specialized broaching operations or gear shaping processes, with tolerances measured in tenths of thousandths of an inch. The surface finish requirements are so stringent that they often require superfinishing operations to achieve the necessary fatigue resistance. Here's where things get really interesting: the bevel gear section that changes the power transmission direction by 90 degrees. The bevel gear teeth are generated using specialized bevel gear cutting machines. Unlike straight cut gears, bevel gears require complex 5-axis machining to create the precisely tapered tooth profile. The cutting process uses a face milling approach, where the cutter head follows a complex path to generate each tooth. The machine must coordinate multiple axes simultaneously while maintaining exact tooth spacing and profile geometry. The quality of this operation directly affects the helicopter's noise, vibration, and harshness characteristics, critical factors in both pilot comfort and mechanical longevity. The heat treatment process for helicopter components is extraordinarily controlled. These shafts undergo vacuum heat treatment to prevent any surface contamination that could initiate fatigue cracks. The carburizing process creates a hard, wear-resistant surface while maintaining a tough, shock-resistant core. Temperature control during heat treatment is maintained within ±5 degrees Fahrenheit, and the cooling rates are precisely controlled using computer-monitored quench systems. The final tempering operation optimizes the balance between hardness and toughness, with hardness testing performed at multiple locations to ensure uniformity. The quality control process is mind-boggling. Every shaft undergoes 100% magnetic particle inspection to detect any surface cracks. Ultrasonic inspection verifies internal integrity, and dimensional inspection using coordinate measuring machines ensures every feature meets aerospace tolerances. The most impressive part: dynamic balancing testing that simulates actual flight conditions. These shafts are spun at speeds exceeding operational requirements, while sensors monitor for any vibration or imbalance. Fatigue testing subjects components to millions of load cycles to verify they'll exceed their service life requirements. Each shaft receives individual certification documentation that travels with the component throughout its service life. This traceability ensures that if any issues arise, they can be tracked back to the exact manufacturing conditions and material lots. From raw aerospace steel to flight-certified perfection, Eurocopter's manufacturing process demonstrates that when lives are on the line, there's simply no substitute for precision engineering and rigorous quality control.